Example reads, an adiabatic pump is to be used to compress saturated liquid water at 10 kPa to a pressure of 15 megapascals in a reversible manner. Determine the work input using entropy data from the compressed liquid table, using the inlet specific volume and pressure values, and average specific volume and pressure values. So basically, this problem is asking for you to find the work input for an adiabatic reversible pump, which basically means isentropic pump. So with the schematic there already done, we can go ahead and draw some assumptions. Assume one, that this is the steady flow problem. Two, the potential and kinetic energy change of the fluid is zero. And three, it is isentropic. Again, because they said, if you look at the change in entropy, again, is the sum of the heat transfer terms plus the sum of the mass energy, or sum of the mass of the entropy being carried in by mass, minus the sum of the entropy being carried out by mass, plus the amount generated. All this will be in rate form. It's adiabatic, so no entropy transfer by heat. It's reversible, so no entropy generated. And all that's left are the mass in and mass out terms. And if in order for, there's no other way for entropy to be generated other than the change in and out. So the result has to be that if I'm going to make it so that the entropy change is zero, the mass, the entropy in by mass has to equal the entropy out by mass. So this ends up becoming an isentropic process. So for part A is asking us to find the work input using the entropy data from the compressed liquid tables. Right, so again, let's go ahead and we'll look at state one, or not state one, but the entropy, or the state of the water entering into the pump, and it says that it's at 10 kPa at as a saturated liquid water, which means a quality of 0. If you go to the tables, right, or basically you can also use ease. You're trying to find the work in. If you remember, the work in for a reversible heat, or for a reversible pump, is going to be, the specific work in is going to be the enthalpy coming out during the isentropic process minus the enthalpy going in, or it's equal to nu delta P. Now the first part is asking you to find the minimum work associated, or the reversible work associated with using the change in enthalpy. So if we have two properties going in, we can get the enthalpy going in for the pump, 191.8 kilojoules per kilogram. From there, we can also get our entropy, 0.6492 kilojoules per kilogram Kelvin, as well as a specific volume going in, since we're going to have to also figure out what the reversible work in, or what the isentropic work of the pump is for using specific volume times the change in pressure. That would be 0.00101 meters cubed per kilogram. And remember, for a pump, reversible work in is the same thing as minimum work in is the same thing as isentropic work, right? That's, those terms, as far as we're concerned, are all interchangeable. So that's state one. That's the state of the water going in. State of the water coming out, we're given the pressure coming out is 15 megapascals. And then we have the entropy coming out is equal to the entropy going in. Right, so if we go ahead and use entropy as a second property, we know that it's 0.6492 kilojoules per kilogram Kelvin. And we can use that to find the enthalpy coming out of the pump if the process were isotropic, 206.9 kilojoules per kilogram. So in this case, the work into the pump will equal the enthalpy coming out if it were isotropic minus the enthalpy going in, right? So this would be H1, this would be H2. So the work per mass ends up being 15.1 kilojoules per kilogram. That is for part A, which was again asking us to use the entropy data from the compressed liquid table, or you're also welcome to use EASE, an engineering equation solver. Now for part B, it's asking you to find the work done using the inlet specific volume and pressure values. This is the inlet specific volume. These are the pressure values, right? Again, the minimum work or the isentropic work of a pump can be computed using the change in enthalpy if the process were isentropic, or also as nu delta P. So if we were to use for part B, we would find that the work in for the isentropic process, right? So I'll specify isentropic is equal to nu going in times P2 minus P1. We have nu 1. We calculated that from the prior slide by looking at the state of the water going in, and we have the two pressure values. We plug that in. We also get 15.1 kilojoules per kilogram. And again, you must understand that this is only valid for an isentropic process of a pump. Right? Only valid for an isentropic process of a pump. Understand that for a non-isentropic pump, H2 actual minus H1, right? That is the actual work of the pump. That would be the actual work of the pump. So H2 minus H1 is going to be greater than nu delta P. The purpose of this problem was to show you that nu delta P, nu 1 times delta P, gives you the same value as H2S minus H1.